In this video, we will be looking at batteries. Now, batteries, I guess, don't need an introduction itself. They have become a very important part of our day-to-day life, and we use batteries in many shape and sizes in different applications, such as our TV remote, smartphones, laptops, and even in our transportation, such as electric cars, buses, etc. So, in order to deal with the batteries, we need to have at least the basic understanding of how they work, how they have been developed over these many years, and what are the safety concerns related to them. So that's why we can design better battery packs and curb the hazards like fire hazard, etc. Now, while studying about these batteries, we will focus on their automobile applications in general. So it is even more important for the EVs. When you are developing or when you are working in EV, it's very important you have the basic understanding of the batteries at least. And with the governments have been pushing with incentives to go towards greener mode of transportation, and certainly electric vehicles play a very important role there. So in general, when we talk about EVs, we are talking about xEVs. So what are xEVs? So here 4 categories comes out. One, hybrid electric vehicle. Now in case of the hybrid electric vehicles, we have a battery plus at least one other source. Now that other source can be your petrol, it can be your diesel, and it can be CNG as well. So there, when we have one battery, when I talk about one battery, we are talking about we have motors, we have converters, etc. as well. So depending on the mode you are in, either you can go completely on battery, but usually the range is very short. So on purely on battery, your range will be very limited, say 12 kilometers or 20 kilometers or something. Okay, so now the next one after the hybrid electric vehicles or HEVs, we have plug-in hybrid electric vehicles. We also call them as PHEVs. They are nothing but the hybrid electric vehicles only, but they have a slightly larger battery pack and which can be charged externally. So the one difference between hybrid electric vehicle and plug-in hybrid electric vehicle is that you can charge your battery pack in case of the PHEV or plug-in hybrid electric vehicles, while in case of your hybrid electric vehicles you cannot charge the battery. Okay, obviously the battery is slightly larger, and with the larger size of the battery comes the large extended range. So you have now more range compared to your normal hybrid electric vehicles. The next category is extended range electric vehicles, and as the name suggests, they will have even larger battery packs compared to the plug-in hybrid ones. So they have more range compared to their both counterparts, their hybrid electric vehicles and plug-in hybrid electric vehicles. The fourth or the last but not the least category is the battery electric vehicles or BEVs. Now they are purely electric vehicles, they don't have any other energy source. So they are not powered by petrol, diesel or CNG, anything. They are completely purely powered by electricity. So these kind of electric vehicles will have only one battery, or the whole vehicle will be powered by that battery pack only. They can have a separate battery pack for auxiliary systems such as your instruments, turn indicators, headlight, etc. in the form of your traditional 12-volt battery, but we'll talk about that later. Okay, now the one important thing to take away from the slide is that all of these battery packs are large, they are high voltage, and they are high current. Now this is where the understanding of the battery becomes very important, because in case of your smartphones you have very small battery pack. Even in case of your laptop you have very small battery packs when you compare them with your transportation or electric vehicles. So the car will have significantly larger battery pack, significantly higher voltages, and significantly higher current as well. Okay, so with this in mind, we'll move on to the next slides, and now let's just start with the basics. So the batteries can be classified into two major categories. They are being primary batteries and secondary batteries. Further, they are distributed along subcategories such as their construction, chemical compositions, their physical attributes like the size, shape, etc., and then their performance. Then obviously the terms like voltage, amp hours, C rating, etc. All of these definition we will look for, we will take a look at all of these definition in the upcoming slides. Then we have the charging and discharging characteristic. This is also something we will talk about in the later on slides. Okay, so to begin with, let's start with the battery terminology first. And in the battery terminology, we have these many definitions like cells, batteries, nominal voltages, etc. etc. We'll look on each of these definitions one by one now. Okay, so the first one is the cells. Now, cells being the smallest individual electrochemical unit. Now, what is the electrochemical unit? Is basically your cell stores the electricity in the form of electrochemical energy and then converts that thing into your pure electrical energy and then transfer through the circuit. Okay, so they deliver a voltage that depends on the cell chemistry entirely. So whether you have to name a few, we will look at the battery chemistries as well, but to name a few, if you have lithium iron phosphate, LiFePO4, which is like one of the newest ones or the safest one, I must say, in the lithium ion family. Then the very tried and trusted lead acid ones, which we already use in our day-to-day petrol and diesel electric vehicles. Okay, so cell, you can say that cell is the smallest individual part or the smallest individual component. Okay, so and they will deliver a voltage, and yeah, as I said, depend upon the cell chemistries. Now there are two types of cells. One can be said as the primary ones, the other ones are the secondary. The difference being the primary ones are the single use cells while the secondary ones are rechargeable. So you can recharge your cells and then use them as again and again instead of a single time use. So now to give a context, your any AA, AAA cells which we use in our TV remotes and etc., wall clocks, etc., they are like single use ones. So they are the primary cells. So you use them once they are out of charge and you cannot no longer use them. You just they are disposable ones. So you just throw them out, take the new ones, and use your appliances. Now the secondary ones are a little bit different with that. As I said, they are rechargeable ones. They are more complex than the primary counterparts. So they will require your charging, discharging circuitries and etc. Okay. So now one important thing is that cell is a different from battery. Okay. So how cell is a different from battery is because battery, as we will see in the battery slide, they are made up of group of cells, while the cell is the smallest individual unit. Okay. So it is important to understand this at the very early stage itself, because even if it is a single cell, sometimes we refer it as a battery, and which can lead to a little bit confusion. So the term battery here now onwards, I will try to use cells for a single unit while batteries for the group of cells or multiple units. Okay. So now let's move on to the next one, batteries. Batteries or the battery packs, they are made up of group of cells. As I said in the previous slide only, that cells is a single individual unit while battery is made up of group of cells connected in series or parallel combinations. Okay, so what is this? What is series combination? What is parallel combination? Or what is both? We will see that as well. Now the batteries, sometimes they come in packaged as a single physical unit. So for example, I am just taking an example which you all must be familiar with. So in case of our automotive application, the 12 volt lead acid battery, which we use for auxiliary applications and our petrol and diesel vehicles, they are comprised of 6 2-volt cells which are connected in series. Okay, so don't like bother about the series part. Just think about it as it has 6 cells. Individual they have 2 volts, and as a group they make 12 volts. Okay, so other times now these you can say they are internally connected, so you cannot like visually see them through the battery pack, because casing is all usually in opaque or non-transparent shade, so black, green, whatever, based on the manufacturers. You cannot see the internal connections. So as I said, it is like packaged in a single physical unit. Okay, and sometimes the connections are external, so we'll talk about the external connections in the later part. For now, understand that cells are the single unit while batteries are the group of cells. Okay, now let's move on to the schematic symbols. So these are the schematic symbols for the cells and batteries. The first one is the cell, as you can see, the single unit, and the battery. So you can see that these are made up of cells only, but it is in a stacked manner, or it is not very clear that whether it's series, whether it's parallel or something, but yeah, you can say that if you have to use a schematic representation, the cell will be this one while the battery will be the other one. Okay, now let's move on to nominal voltage. Now these are the few terms which we are going to keep on hearing very frequently from here now onwards. So let's just get the definition correct here only. Okay, so what is nominal voltage? So the cell voltage usually depends on the combination of their chemicals which are used inside the cell. Okay, so now these cells are anode, cathode, and when we will talk about the functioning of the battery, we will talk about anode, cathode, separator, electrolyte, etc. in detail. But for now, you can say that this nominal voltage will depend upon the active chemicals. So obviously it will differ from cell to cell. So if you are using a different combination of chemicals, then you are going to get the different nominal voltage. We'll see about that. Usually for lithium based cells, this is over 3 voltage, so 3.7, 3.5, 3.3, again depending on which type of chemicals we are using. Okay, so the next one, usually these terms are printed on the cell packaging itself. So if you have a single cell, you can see on this packaging that it sells a nominal voltage of 3.3 volt or and the capacity as well. Okay, now one thing to keep in mind is that the cell voltage under load is different, and this nominal voltage is more of a typical or the averaged out voltage per se. So it is not exactly what the cell can deliver. So there will be upper limit, there will be a lower threshold, and we will see what are they. And so, but in general, you can say in order to keep it simple, we use nominal voltages. Now the next one will be the nominal capacity. Similar to the nominal voltage, nominal capacity is again based on the chemistries only or the dimensions as well. So same chemistry but different dimensions, nominal capacity will be different. Okay, so say for example it has a more diameter or it has a shorter length, then your nominal capacity will vary. Now this nominal capacity will specify the quantity of the charge that the battery can hold or you can say the cell can hold. So the individual cell, how much quantity of charge it can hold is defined by its nominal capacity. It's usually in ampere hours or Ah or milliampere hours or mAh. So now again come back to if I come back to the smartphone or the basic example. So smartphones, you have heard that they have 5000 mAh, 7000 mAh, or some of the tablets will have 8000 mAh, 10,000 mAh of capacity. So this is the nominal capacity. So yeah, now these are the nominal capacity, then the cell is rated to hold that much at least. So again, this is not the exact one but the averaged one. So in order to simplify things, we use the nominal capacity. And now the nominal capacity is also often printed on the cell package alongside the nominal voltages. Okay, now let's move on to the next very important term, which is C rate. Here the C stands for the charge. Okay, so the C rate or the charge rate. Now this is an relative measure for the electrical current. Okay, as I said, the charge means electrons and their behaviors. Okay, so we have charge rate or C rate, and this now let's understand within an example. So for example, if I have a 20 ampere hour cell, and now theoretically, like with respect to if it is a nominal capacity, theoretically it should be able to deliver 20 amperes of current. Now I'll refer to this one as the 1C because the cell capacity was 20 ampere hour. Okay, and for 1 hour. So it is the C rate is nothing but the relative measure which will say that at a constant current charge or a constant current discharge. I will tell you what constant current charge is and what constant current discharge is as well. So if I have to provide a constant current charge for 1 hour, my cell can able to sustain that much of electrical current. So for example, if I have a 20 ampere hour cell, it should be able to deliver about 20 amps of current for 1 hour, and if I have to draw only 2 amps, then my C rate will be 1/10 of that one. So if I am drawing 20 amps from a 20 ampere hour cell, I'm drawing the charge, I'm drawing the electrical current at 1 C, at the rate of 1 C. If I'm drawing only 2 amps out of it, which means I'm drawing at 1/10 of it. So if my battery was about rated to sustain 20 amps of current for 1 hour, now if I'm only drawing 2 amps, which is 1/10, so my hours should increase, right? And now the factor will be 10 only, because I'm reducing my withdraw or discharge or charge from the battery by 1/10. Okay, now this relationship not as I said, this is, I'm talking about theoretical one, so the relationship is not strictly linear in terms of that, but yeah, for example, for a simple understanding, you can say 1C means if I have a 20Ah cell, I'm drawing 20 amps, I should be able to draw it for 1 hour, and if I'm drawing anything less than that, so I should be able to draw more than that. Or for example, if I'm drawing 40 amps, which means I'm drawing at a 2C, at the rate of 2C, then I should be able to last, the battery cell will last only 30 minutes. Okay, so there is something called as specific power as well, that is a little bit complex term, which we will tackle a little bit later in the video. Okay, so now let's talk about the constant current. Okay, so here we have an example here. So here the blue lines represent constant current, and the dashed line represent constant power. Also you can see the CV. Now I'll tell you what CC and what CV is. Okay, so here in the first left hand side, first graph, you can see voltage versus time. Now here time to do, what I'm trying to do is I'm trying to charge the battery pack. Okay, now all of these curves are for charging only. Discharging will be exactly opposite. So let's just first look at the charge, and later on we will see the discharge one. Okay, so during charging you can see that how my cell voltages are behaving, so with respect to time. So at 500 seconds my cell voltage is that much, and roughly for the first graph at 1500 seconds you can see voltage stops increasing. So you don't see any increase in the voltage, rather it stays constant, which means earlier it was constant current, later on, like after 1500 seconds of time, it have become constant voltages. Okay, now just compare the left hand side graphs. So the upper one and the lower one, both of them, now all of these are from a single cell only. Okay, so now let's just focus on the first part, so the left hand side part, upper and lower. The first graph shows the voltage versus time, while the lower one shows the current versus time. Okay, so now you can see initially the current graph was particularly flat, later on it started increasing and came to again a flat curve only. So that was what was happening. Earlier it was under constant current, so constant current was throughout constant. Later on it moved to the constant voltage. Okay, so now it moved to the constant voltage, and now it started to, like, ampere started to drop. It became like came to nearby 0, and then my voltage started to flatten out. Okay, so this is what happens when we usually have constant current and constant voltages. So you understand that constant current is nothing but your current rate will remain same versus time, and for constant voltage your voltage will remain the same over time. Okay, now the other two are the constant power and constant range. So here in the first graph we had voltage, then we have current, then we have power, and then we have SOC. So SOC is nothing but your percentage over time. So it started from 50, and over the time of like 50% or something, it came to 90, and then it went very slowly. Okay, now these graphs are for representation only, in order to like give you a basic understanding first. So they are not they don't come from any, they obviously do come from a lithium-ion family only, but cell chemistry and their capacity, that's not a concern as of now. Okay, Now, as I said, I'll talk about energy and power as well. So what is energy? Energy is nothing but how much the cell can store in the electrical form. So obviously you are trying to store your whatever the energy is already present. So if for example your electric vehicle, when you are charging, you are drawing current from one source, which is your electrical grid, and you are trying to store that energy inside the battery pack of your electric vehicle. Or in case you are charging a smartphone, you are trying to harness or trying to store that energy inside your smartphone for a duration of time, say for example 8 hours or 1 day, I can say. In that manner, the energy will be the one that how much your cell can store. So to understand this, the total energy is roughly you can say multiplied to your nominal voltage multiplied by its nominal capacity. Now again your units are in that manner only. So the voltage, so your nominal voltage, and then we have the nominal capacity. Your nominal capacity is usually in Ah and your voltage is volts. Okay, now when you combine them, you create energy. Now energy is in terms of watt hours, while you are trying to produce some power. So we will talk about power as well. So let's just understand in this in a manner that for total nominal, if you have a battery pack which is like rated for a storage capacity of 3.7 volts, and its nominal capacity or the nominal voltage is 3.7 volt, nominal capacity is 1.9 ampere hours. Now the battery will be 3.7 times 1.9, which makes it 7.03 watt hours. So your total or your nominal energy storage capacity will become 7.03 watt hours. Okay, so now as I said, this is purely based on your nominal voltage and nominal capacity readings. Now the total energy or will be 7.03 watt hours. And now this cell can produce like how this cell can produce instantaneous power will be based on watts only. So as I said, your cell was able to provide 20 amps of current for a period of 1 hour. That's why we called it 20 Ah, right? Now for the instantaneous term, so for within that second or within that instantaneous moment, how much power your cell can provide is the specific power. So your specific energy, your energy is the one which is the multiplication or the product of nominal voltage and nominal capacity. The energy is the and the power is the rate of energy release at that particular instant. So for example, if I say I have you can have a power draw of 1 kilowatts, which means that you can draw 1 kilowatt of instantaneous power from that cell. Again, a hypothetical term only. Now let's move on to the next slide, which is cells connected in series. So if you remember from the earlier one, at the very beginning I told that cell is the smallest individual unit. Now batteries will have group of cells. Now usually these cells are connected in either series or parallel or sometimes both. Okay, so when cells are connected in series, the voltage is the total battery voltage is the sum of their individual cell voltages. So for example, if you have a battery pack of 4 volt, which means either now the combination will be you can have 1 volt battery connected in four 1 volt batteries connected in series, 2 1 volt batteries connected, 2 volt batteries connected in series, which will give you the total battery voltage of 4 volts. Okay, now while you are connecting them in series, your battery capacity will not be altered, so it remains the same. So if I had a 1 volt 10 Ah battery, I am connecting them in series, so 1 volt 10 Ah plus 1 volt 10 Ah, now my battery pack becomes 2 volts 10 Ah. Okay, so that's why now why this happens, because the same electrical current passes through all of the cells, be it charging or discharging, and also at the same rate. So there is no change in your battery capacity. So let's just understand with this example. As I said, if we have now, so you can see here 3 battery cells, okay, 3 cells, and now this is making a single battery. Now you can like clearly understand how they are connected. Their terminals are interconnected, so the positive, negative, negative, positive, positive, negative, etc. Okay, so now for the battery design with the 3 volt 10 ampere hours of cells which are connected in series, now you will have a nominal voltage. As I said, in series nominal voltage is multiplied and the nominal capacity remains the same. So your nominal voltages add up, 3 times 3 makes it 9 volt, and your nominal capacity remains the same, which was earlier 10 Ah, now 10 Ah only. Now the total energy capacity of that battery pack becomes your 9 volt times your 10 ampere hour, so 90 watt hour. Your total battery capacity or the total energy capacity for that particular battery becomes 90 watt hours. So let's move on to the parallel now. So for example, if you have again in series your voltage was increasing, in parallel your capacity will increase. So okay, so yeah, the simple thing, in case of the series voltage adds up, in case of parallel capacity adds up. So when cells are connected in parallel, battery voltage is equal to the cell voltage and the battery capacity is sum of all of their capacities. So let's just understand with another example here. Here we have cells connected in parallel, okay, and you can see I have connected 5 cells in parallel here. So do you understand the connections now? In case of your series connection, your terminals were like positive was connected to negative, negative was connected to positive, in that manner, okay. But in case of your parallel ones, all of the positive terminals are connected in one side while the negative ones are connected in one another side. That's how you create a parallel connection. Now let's get back to our example. So 5 3 volt 10 Ah cells which are connected in parallel, which means your nominal voltage remains the same, so nominal voltage will be 3 volt only. Your capacity will increase to now 5 times your 10 Ah, which means 50 Ah. Now the total energy capacity will be multiplication of your voltage and capacity, which is 150 watt hours. Okay, now if you connected your cells in series, now you understood, you get an idea that if you connect cells in series you are increasing voltage, if you connect cells in parallel you are increasing capacity, and based on your requirement, how much voltages you need, how much capacity you want to have, you can play around with series and parallel combinations. Okay, now let's move on to the chemistries. So I'll just give you a brief about the chemistries and how they have developed over the recent time. Okay, so now you can see here we have on the x-axis we have specific power, which is nothing but, now when you compare them with their weights. So for example, if I have a 10 kg capacity, 10 kg battery pack, now this how much power it can hold, watts divided by the kg will give me a specific power, and the energy from the earlier definition only, specific energy will be watt hour per kg of that battery, whatever chemistry I am using. Okay, so now on the x-axis you can see you have specific power, on the on the x-axis, I'm sorry, pardon, on the x-axis you have specific energy which is in watt hour per kg, and on y-axis you have specific power which is watts per kg. Okay, so now we start with the lead acid ones. Lead acid ones were the very first type which are very stable and commonly used. Even nowadays, because of their simplicity, we use in our normal ICE or internal combustion engine vehicles like petrol, diesel, etc. Okay, in some electric cars as well, they are still use lead acid in order to have auxiliary systems, to run our auxiliary systems. Okay, so now you can see a particular trend here. Okay, when we move from lead acid, so now okay, let me just explain this one first. So lead acid, or then we have NiCd. Now NiCd is nickel cadmium. Then we have NiMH, which is nickel manganese hydride. Then we have lithium ion, and then we have the potential of lithium metals. Okay, so when we move from lead acid to nickel cadmium, you can see that we are increasing both. We are increasing a specific power as well as we are increasing a longer run time. So why it is very important? See, because that's why I am taking a specific power, not just power, specific power, and not just energy, specific energy, because See, in case of your moving applications like your transport, in case of transportation, so electric vehicles, electric car, bus, bike, etc., you are going to carry that weight. Okay. Now what happens in ICE vehicles, your petrol engine vehicles, is that as you move on, you burn that fuel and your vehicles becomes lighter, lighter and lighter. Okay. So if, for example, if you start with a 50 liters of fuel, after a certain period of running, you are going to run out of fuel. So you're losing that 50 liters of weight. So whatever the density, you can multiply 76 0.6 multiply, and then you will get the weight of that particular fuel load, whatever you're carrying in. Okay. So as you're running on, you're using that fuel and you're depleting that, you're depleting your fuel tank, which means you're emptying out it. Okay. So but in case of the battery packs, you start with the same weight, 10 kg, you end up with the same weight. So that's why it becomes very important for us to understand that how much is the specific power and how much is the specific energy for that particular cell chemistry. And now as the development, so we started with lead acid, then we moved on to nickel cadmiums, then we made developments on lithium metal hydrides. They all like address their previous. So lead acid had some pros and cons, nickel cadmium tried to address those cons. Now there were some cons for the nickel cadmium as well because of the lead content. So they can now, or the cadmium content, then they moved on to nickel metal hydrides to completely get rid of the cadmium content. But then again it had own problems or cons, I can say. So then we moved on to the next one. So we moved on to lithium ion. Now lithium ion family, which tends to be, as you can see, it was quite a leap from lead acid ones, and even from the nickel metal hydrides as well. So they had higher current and they had longer run times as well. So as you move on in the x-axis in the positive direction, you are going to get longer run times, and if you are moving towards in the y-axis, upwards in the y-axis, then you are going to have higher currents as well. So your lithium ion provided higher current and longer run times. That's why it became that's why lithium ion became so popular, and we are using it almost in all of their applications. Your smartphone have lithium ion cells, your laptops even have lithium ion cells only. Okay. So now there is obviously there is nothing called as the perfect battery. Okay. So all of, doesn't matter whatever combination you take, be it lead acid, be it lithium ion, even lithium ion have their own different types. I will talk about it later. They are basically, there is just a difference between what type of electrode they are using, what is anode, what is cathode, and what are the electrolytes. So we will talk about in the next section. So yeah, so there is definitely potential for lithium metal ones. Now these are they are definitely they are improvement over the lithium ion counterparts. They are supposed to have higher current and they are supposed to provide us more longer run times as well. So it's now the lithium ion is still in the research phase, and there are some prototypes available, but there is yet to have commercialization for that particular chemistry. So lithium ions becomes a potential or area of improvement over lithium ions. So yeah, even we have metal air batteries as well. So metal air batteries will be another improvement over their lithium metal ones. Okay. So yeah, in the now onwards we are just going to focus on the lithium ion only, because lead acid, nickel cadmium, nickel metal hydride, even though they are not used to such an extent of lithium ion ones. And when we talk about electric vehicles in general, as I said, we started with xEVs. Okay, so be it hybrid electric vehicle, PHEV, range extended ones, or your classic pure electric vehicles, pure battery electric vehicles, all of them will use in some case or some type of lithium ion family only. So now we will just focus towards the lithium ion part. Okay.